So folks, we'll be a little more careful in developing these definitions in class, and that will mainly mean going through these images a little more carefully. But let's go ahead and give the limit definitions of the partial derivatives. So this can be extended to any number of independent variables for a multivariate function, but we'll just do it for a function of two variables. So if we want to talk about the partial derivative of the function with respect to the variable x at a point a, b, how would we go about finding that? So again, we're going to look at this first image here for our limit definition where we have fixed the value b, and we're going to nudge a by some amount h and ask what is the rate of change in that direction. So the limit definition is the limit as h approaches 0 of f of a plus h comma b minus f of a b all over h. And this should look like your difference quotient, and you'll notice that f of b, or the y coordinate, is the same in both cases. Of course, you can write a limit all you want, but as we saw in the previous section, it doesn't actually make sense to write the limit if that limit doesn't exist. So we always have to add, provided the limit exists. Otherwise, the function is not differentiable at that point. So the partial derivative of f with respect to y at a point a, b is what? It's going to be the limit as h approaches 0 of f of, here we're going to leave a the same in both cases, and nudge the y coordinate slightly by amount of h, and look at that difference. And so this is again provided the limit exists. So folks, we'll explore that a little bit more in class, but let's give some notation for this. So the first type of notation that I want to give is the partial derivative notation. So we're going to read this symbol as a partial or partial derivative. So if I want to talk about the partial derivative at a point, I might write the partial derivative of the function f with respect to the variable x at the point a comma b. Or another way I could do that is to say the partial derivative of f with respect to the variable x at the point a comma b. That's another way of doing so. Okay. So we could talk about the partial derivative as just a function, in which case we talk about partial f partial x. This is the derivative of the function f, but it's a partial derivative, meaning we obtained it by asking, as we leave y the same, how do the x values change as we nudge over in a little direction? There's some other notation, though, to make sure that you know, and this is another form of the notation to say that the partial derivative of f evaluated at a, b taken with respect to x. So this is the partial derivative of f with respect to the independent variable x at the point a, b. That's how you would read this. And just as a function, we would just write f sub x or f sub y. Okay. There's some other notation, and I'll show you that here. We could say d sub x of ab. So this says, excuse me, let me write it this way, d sub f of ab. So this is the partial derivative with respect to x of the function f at the point a, b. Or we might just write d sub f of x. So this is the partial derivative of the function taken with respect to x, or d sub y sub f. Or here we could have d sub y of f of a, b. So these are our derivative notations that we'll be using, and we'll see that sometimes one form is more usable than another. Okay, so let's actually compute some partial derivatives here.